I'm just here to introduce the main attraction. I'm very excited to do so. I think I haven't met our speaker, Priya, before, so we've had a little chance to talk this morning. Very interesting person, so I think you're going to enjoy this morning. So I've been very honoured to be invited to do this introduction, especially for such a great scientist and a great author and actually a science communicator, which we think is very important. One could argue that if the power of a good story, the power of good literature, is it's an ability to subtly and slowly introduce the characters. Instead of telling you everything about them up front, there's gaps left so that you can use your imagination and your own experiences to fill in those gaps and to fill out the story so that the author can be a little bit more subtle and doesn't have to do that for you. So the reader is left to fill in those gaps and create their own version and their own involvement with the story. And it's often not what the author reveals about the character in a given moment or the event in the given moment that defines the whole story. It's the path of the characters and the forces that shape that path. So it's fitting that our speaker this morning will tell such a story whose principal character is the light from distant stars, a character whose true history and nature are slowly revealed through the interactions with the universe around her. This applies to magic things called dark matter and dark energy, and the even more magic things called black holes. So as the arc of the story unfolds, the mysterious journey of this stellar light slowly but inevitably reveals its secret, and we find that there are hidden characters and forces shaping this journey from its home star to the observer's eyes. And like all good stories, the universe is richer and more complex than it first appears. This unseen complexity is the dramatis persona that shapes the life of our character, and through this reveals the true nature of the universe. It's my great honour to introduce our speaker this morning, Professor Priyamvada Natarajan, to tell us the mysterious story of the universe and how its secrets are being revealed. She's only going to tell you a little bit, a small part of the universe. It's a big place. Professor Natarajan is a theoretical astrophysicist from Yale University with a passion for cosmology, black holes and dark matter. She holds the Sophie and Tycho Brahe Professorship of the Dark Cosmology Centre Niels Bohr Institute at the University of Copenhagen, and has been recently elected to an honorary professorship for life at the University of Delhi in India. She received her undergraduate degree in physics and mathematics from MIT, a master's degree from MIT's program in science, technology and society, and her doctorate from Trinity College, Cambridge, where she was the first woman in astrophysics to be elected a fellow. That's not an easy thing, and so that's a great honor and well deserved. Dr. Natarajan is a recipient of a number of prestigious fellowships, which I really shouldn't take time to read because you want to hear the speaker, but it includes a Guggenheim Fellowship and an Emmeline Bigelow Conlon Fellowship. She was also appointed as a visiting professor at the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. And it goes on. You're in for a treat here today. Priya was the 2009 recipient of the India Abroad Foundation's Face of the Future Award. She was also the 2009 recipient of the Award for Academic Achievement from the Global Organization for the People of Indian Origin. She was elected a Fellow of the American Physical Society and a Fellow of the Explorers Club, both in 2010. And finally, in January 2011, she was awarded an India Empire NRI Award for Achievement in the Sciences in New Delhi, India. Very accomplished person, absolutely wonderful scientist, and a great speaker. Please join me in welcoming Professor Priyamvada Natarajan to discuss the enigmas of black holes.
Thank you so much. Thanks so much, David, for that very kind introduction. We're desperately searching for where I put the slide advancer. I think it's on the table. It's a real pleasure and honor to have the privilege of sharing with you some of the exciting new results that you probably have been seeing in newspaper headlines. Especially black holes have made a major comeback and onto the astronomical stage. And also I want to share, hopefully, my sense of passion and childlike excitement at the work that I am so fortunate to have the opportunity to do. So what I want to start with is to give you a little bit of a context. So as David mentioned, the universe is replete with all kinds of intriguing constituents. And constituents that we now have a very good idea of what they are. So we know that the universe is dominated by matter that is not ordinary matter, not the stuff that we are made of, ordinary atoms, but some other exotic stuff that was created most likely very early on in the universe that's called dark matter. And it is as yet directly undetected, but it has been indirectly inferred. Its presence has been indirectly inferred from the bending of light and the fact that it's matter, it has gravity, so it exerts gravitational influence. So it is there, it's not like ether, it is there, but we are just yet to discover the actual particle that is dark matter. Then the universe is actually dominated by something that's quite mysterious, which is called dark energy. And you might see the pattern emerging here that when we don't quite know what it is, we append dark to the front. So that is sort of true. And so dark energy, we know once again, we know what it does, we don't know what it is, much like dark matter. And we believe that the accelerating expansion of our universe is actually powered by this mysterious force that is dark energy. And it was very recently discovered, just to give you context. 1998 was the first discovery of this entity and what it does, because that was when the accelerating expansion of the universe was discovered. We knew the universe was expanding from Hubble, from very early on, from the 1920s and 30s, but this is very brand new. The fact that, and we also know that black holes, they don't punch their weight in terms of the mass repository of the universe, but they definitely have outsized influence on shaping the universe. And that understanding has really emerged in the last 10 to 15 years, the fact that they play a very important role in the universe. So by mass, they're not as important as all the stars that we see in the universe, which, once again, compared to dark matter, are not that important either. So everything that we are made of, every atom, everything in the periodic table is less than 4% of the cosmic inventory. So talk about being insignificant and significant at the same time. So before I talk about black holes and introduce you to black holes, and I just wanted to give you a little more context of how we see the universe and their role. And I've talked about how we infer the presence of dark matter and dark energy by what they do. Similarly, for black holes, we don't actually see them directly. We see them indirectly, as I will show you in a little bit. But before that, I need to kind of give you the context of how we model and think about the cosmos. And that is attributed, this particular sort of reformulation, it was a fundamental reformulation when it happened. And that was wrought by Albert Einstein and his theory of general relativity. So what Einstein actually really did with a profound insight was the relationship between geometry, that is the shape of space itself, the constituents of the universe, so the shape of the universe, the constituents of the universe, and the evolution of the universe. So these are the three big aspects. So he was able to unite the geometry, the contents, and the fate of the universe. And that's one of the reasons why, his theory has been so comprehensive. It's had such far-reaching implications for many, many aspects of astrophysical phenomena. And strangely enough, he's come out, all the tests of his theory so far, given the accuracy to which we can make measurements, it's holding up really rather well, remarkably so. So in Einstein's reformulation, so you might all remember, right? This was a reformulation of Newton's theory of gravity and this sort of idea of the relationship between matter and how matter moves. The theory from the 1600s was really Newton's theory. And that's what Einstein radically reformulated. So in Einstein's version of what the universe is, and now this is the accepted version, the universe really is a bendable sheet. It's a fabric. You can think of the universe as a fabric. There's nothing above it. The entire universe is this fabric. Minor detail, it's 4 dimensions, but let's gloss over that for the moment. Let's just think of it as a sheet. And what matter really does is create little potholes in this sheet. So no matter what matter it is, whether it's a tiny little rock, a planetesimal, planet, star, galaxy, lump of dark matter, you are creating a little pothole. And as I told you, there's nothing above this sheet. This is the universe. We are all embedded in it. So light has to travel along this sheet. Any information in the universe travels along this sheet. And so light is our cosmic messenger. So light from any distant object, while on its way to us, encounters each and every pothole, and that alters properties of the light. So there's an imprint of all the potholes that it encounters. And that's how we know about dark matter. And as you'll see, that's how we know about black holes as well. So that's one of the key ways. So it's very fundamental to our understanding of how light propagates in the universe, this whole reformulation. And of course, what is fundamental is the relationship, the why of gravity. Why do we have gravity? We have gravity because matter interacts with space in this very particular way. It alters the geometry of space, right? And so you can see that, a heavy object like the Earth, the sun, will all cause these inundations. So you might say, okay, what is the connection of Einstein and black holes? So Einstein's theory of general relativity then will predict the shape of space, the distortion that is produced by any lump of matter. So those are his field equations, and those are the solutions. And it turns out that one very simple solution is a very dense, compact bit of matter that would cause an extreme puncture. The pothole is really deep. I mean, as I often joke, it actually rivals and is deeper than any pothole on my local I-95, which is constantly under construction. So this is the interstate highway near where I live. And the potholes, I got this eureka moment about this analogy because of driving through those potholes all the time. But you see here that these are the predicted distortions in the shape of the universe, the shape of space, by different kinds of matter distributions. So if you have no matter in the universe, this sheet would have been flat. And that's not the case. We know that we have matter in the universe. We are here. So the sun, notice the divot, the small pothole that the sun causes. Then you have neutron stars that are very dense. They're very tightly packed. They're less fluffy than the sun. So look at the pothole. It is deeper. So it turns out that a black hole is so compact and so dense that it creates a puncture in space-time. So hold your horses and don't ask me if you puncture, where are you going into? That's for the Q&A. But so it causes a very, very deep pothole. And so the distortion effects, as you can see, of any light that strays close is going to be pretty dramatic. So one of the reasons, so the black hole solution, the idea that a compact mass would do this very extreme distortion was found, this solution, it was a solution to Einstein's equations, it was actually found within 6 months of Einstein giving his lecture to the Prussian Academy of Sciences presenting his theory. And it was produced by Karl Schwarzschild, who at the time was fighting, this was World War I, he was in the trenches, he was a physicist, he was in the trenches, he'd heard about the lecture, and he worked it out. Einstein never thought that his complex equations would actually have an exact solution. So when this solution was presented to him, he said, oh, that's great, but it can't be real. It can't correspond to real objects, right? And it turns out that it does correspond to real object, as we'll see. These are very extreme, bizarre, enigmatic, but exciting objects in the universe, given what they do. So I've always been interested in the dark side of the universe. And then eventually, about 4 or 5 years ago, when I started thinking about writing a book, I wanted to write about my research as well as these great scientific ideas in the last 100 years that have gotten currency. Black holes is one of them. And I never imagined that black hole, the term black hole, which actually lead me back to India. It turns out the term originated before it was used in science. It originated in 1756, and it was the name given to an infamous prison where soldiers of the East India Company had been incarcerated overnight, and very few of them made it out the next morning. So they were asphyxiated, many of them died, so it was a point of no return. So that was the origin of the term black hole, which then turns out was a very apt description of these astronomical objects. So this is just a schematic telling you what is crazy about black holes. So what is really crazy about black holes is because of the depth of the pothole, because they cause this puncture in space-time, and as I mentioned before, all light has to traverse through, it turns out that any light that strays close to the puncture that a black hole creates in space-time can never make its way out. So that's why it's black. So a black hole doesn't emit on its own. In fact, what we see, as I'll show you in a little bit, when we see black holes, what we're really seeing are the dying gasps of matter that are getting pulled in by the gravity of the black hole to a point of no return. So they literally are dying gasps because this is just gas matter that is getting heated and that starts to glow thermally. So you start seeing X-rays and optical radiation from the stuff just before it falls into the black hole. Because once it goes in, that's it. You have no information. You know nothing comes back out. However, so black holes are pretty extreme, violent places. So you can see here some toy trajectories that I've shown. So if you have light, it's possible for light to graze past and not get sucked into a black hole. It's possible for light to get completely captured into a black hole, depending on where the rays hit and approach the black hole. And then there's a sweet spot. The sweet spot is actually sort of a sacred boundary almost, and it's called the event horizon, right? And so when light or any matter crosses that boundary, and it's shown as the dashed line here, then that's the point of no return. But anywhere outside, you can have one of two fates. You can either just escape, or more interestingly, you could be sort of in limbo. You could get captured into those light orbits, they're called photon orbits, that are outside this event horizon, and you could be perpetually, it's like Dante's purgatory, so you could be in limbo always. You would be there all the time, right? You'd be captured. And of course, if you get a nudge, you go back in to the event horizon. So this is sort of what really is the black hole is termed the singularity. So where are black holes? Are they real? So I'm going to now convince you and show you that black holes are very real. So we started out with an image of a Hubble Space Telescope image of a galaxy. So it turns out that black holes are harbored in the centers of most, if not all, galaxies, including our own. So our own galaxy harbors a 4 million times the mass of the sun black hole. It's very compact. It's sitting right at the center. It exerts no influence on us. The solar system is way far out, but it exerts a lot of influence right around its vicinity, as we'll see. So what you saw here is we zoomed in from a real image all the way into an artist's conception. We can never quite get this close to a black hole. We never could till very recently. And many of you must have seen the image from the Event Horizon Telescope collaboration that was released this April. And I'll show that to you in a little bit, is why that image was so iconic and transformative, because it points out to having a look at a place that we have never seen before. We never got that close to any black hole before. Okay? So, but it's very well established now that black holes sit in the center, as I said, of most, if not all, galaxies. But it turns out that these black holes that sit in the centers of galaxies, they're called supermassive black holes because they're about 1 million times or more the mass of our sun. And remember, a galaxy typically has 6-7 orders of magnitude more in stars. So in terms of the mass budget of a galaxy, the black hole is a tiny speck. And that's what is so peculiar, amazing, and intriguing about these objects. They are tiny in terms of the mass, but they exert an outsized influence on how the galaxy forms, when the stars form, when it stops forming stars. It's almost like it's a cosmic, enigmatic, central, invisible regulator. Okay? And all of this has just become clear in the last 10 years, the sort of the all-pervasive influence that these black holes exert, despite being right at the center in a very, very sort of innocuously sitting there. But black holes, it turns out, appear to be in two states. They're either fasting or they're feasting. So you have a black hole that is not fed by any matter, it's fasting, either because it has depleted everything that's sitting around it, like the black hole in the center of our galaxy. It is fasting, it's not feasting at the moment, because it's kind of gotten rid, it has chomped all the gas that was already there. So there's nothing nearby, unless a stray star goes nearby, then it can be captured. So, it's sort of sitting there. Whereas there are many galaxies in which the black hole is actively feeding gas, and this gas is glowing as it's falling into the black hole. And these objects are called quasars. They're extremely bright. They're sort of the brightest beacons in the universe. And we detect them out to great distances. So the most compelling evidence for a black hole is the one at the center of our own galaxy. So this is a movie. Hopefully it will start. Often I have to be patient with this one. Yeah. So what you see here are the orbits of stars. This is real data taken in the years that you see passing in the counter below. These are the real orbits of stars right around the black hole. And you saw this blob going past. So this, we believe, was a blob that could have been more dramatically swallowed, and it might have fed our black hole for a bit, but it didn't. So we're hoping it'll come back again because it's caught. It's caught in the gravity. It's going to come back again. So these are future predictions for where this blob might come back in and feed our little fasting black hole a little bit of gas, which we would see then as this kind of, it's called a tidal disruption flare, and we would see that. So the motions of the stars that you just saw in the center of our galaxy that have been mapped point to the existence of a gravitationally dominant object. So you saw all those ellipses close. It might remind you of Kepler's laws, solar system, and the orbits. So there, remember, we know that the sun is the dominant gravitational object in the solar system. And so all the orbits are elliptical orbits around the sun, one of the foci. So similarly, we can infer the mass of the black hole from the orbits that close. So it's really spectacular. And that's how we have a really good mass estimate for that black hole. So then it turns out, as I said, black holes punch more than their weight. So this is a nearby galaxy, Centaurus A, which has an active black hole, and that is spewing out energy, matter in terms of these very large jets, radio jets. And what you see there in sort of the dusty silhouette is actually the galaxy itself, all the stars in the galaxy that you would see in a Hubble image. It's a Hubble image. And what you're seeing in pink and sort of whitish is X-ray and radio data that shows you that radio and X-ray emission from the black hole traverses well past where the galaxy is optically. So it really influences a huge amount of space around the galaxy. So as I said, these guys really punch beyond their weight in terms of being very compact at the center and being so diminutive in terms of their mass. But they alter and they shape the energetics. They pump out energy. They can be very violent, and they do a lot of transformative things to galaxies. And so this is data, and we know that. And as I said, some of the most compelling evidence up close for a black hole came recently from the Event Horizon Telescope imaging of a black hole in M87. And that is a galaxy that is nearby. And this black hole is a monster black hole compared to the one in the center of our own galaxy as well. It's 6.5 billion times. Remember, ours is just 4 million. So it's sort of a piddly black hole in comparison. So this black hole is actually not active. However, because of the deep divot, the deep pothole that this black hole creates in space-time, it distorts light that comes close by very dramatically. And so you can see the light bending, and what you're seeing here, the silhouette that you are seeing here, is that photon orbit, that light orbit where, so this is emission from stuff that is falling in on its way, but the light is kind of captured and trapped, and so we are seeing the silhouette. And the light bending is so extreme, it's almost like you're able to see the back of your head, right? So we're seeing all the light from all around, the full silhouette. That's why it sort of is circular and it closes, right? So this is very, very dramatic. And so this is as close as we have gotten to a black hole in terms of getting direct data. We've always, as we saw, right, we've inferred the presence of the black hole from the motions of stars in the center of our galaxy. That was much further away. So the nearest star to the black hole in our galaxy is about 17 light days away, okay, so at its closest approach. So that graphic that you saw is actually well outside where this image is taken from. So this was really like the cartoon where I showed you the light orbits. That's how close we are in this. And, and this was a major breakthrough. was a major, major breakthrough for many reasons. First of all, as I said, we got really up close to a black hole. Second, of how this project leveraged existing facilities. So basically, it was a very clever idea. There were many radio telescopes on Earth, 8 to 9 of them, that were put together to make the entire Earth behave like a radio dish. Okay, so this is the largest radio dish you could have ever made sitting here. Right, so it was very clever to leverage that. That's what allowed you to resolve at that distance that full silhouette that you saw. And so it was a remarkable international collaboration. It's technically, this was an amazing breakthrough on many fronts, computation, image processing. It just took a lot, and really remarkable. So I was not part of the collaboration. I was just a very strong supporter of it. And so this was the party they had at the Air and Space Museum, and that's the PI of the project, Shep Doleman, who's there. And apparently there was a cocktail called Black Hole before, that predates all of this. So let me quickly now take you to where we are in our current understanding, not of individual black holes, but what do we know about them as a population? Because that's sort of the work that I do. So we know a lot about, we have a good census of these quasars, because I told you they're very bright beacons, so we can see them way out into the early universe. And so what you see in that graph and on your left-hand side, those little dots tell you the quasars that have been detected in the universe. There's thousands of them have been detected. And the x-axis is a measure of the distance. So the bright green ones are the farthest ones. The gray ones are the nearest ones to us. And so what we find now, we know a lot about black holes. We find that, as I mentioned, they seem to be synchronizing the formation of stars in the galaxy that they sit in. So that's kind of intriguing. So that's one of the problems that people like me have been working on for a very long time, which is their measured correlations. So the bigger a galaxy, the bigger its central black hole. And because there is this connection between the formation of stars and the growth of a black hole, we believe that there's a very deep sort of underlying physical laws that regulate this process. And many of us have been trying to figure out, how do black holes evolve? So one of the problems that I have spent the last decade working on is the origin of the first black holes. So we know that some of the first black holes form from the end stars of the first stars that form in the universe. So the end state of the first stars, the remnants, are little black holes. But because you see quasars out so far out in the universe, and these quasars are powered by billion solar mass black holes, these little piddly seeds are not good enough. You don't have enough time to grow them that rapidly, so you need another way to make seeds. And so with my research group, one of the proposals that we made are of this sort of new channel called direct collapse black holes. So these are black holes that would form that would be very, very massive from the get-go. So I've kind of glossed over quickly, say, well, black holes grow. So how do black holes grow? They actually grow in a bunch of different ways. Though you have gas feeding in, so you can have a black hole that is sitting in the center of a very gas-rich galaxy, and gas would trickle down, and that's a sort of image that's a cross-section from a simulation from our research group that you were seeing there. And the gas is kind of going to trickle through. The black hole is in the center. It's that inner point there. The other way black holes grow, as does all structure in the universe, is by collisions of galaxies. We know that galaxies grow by collisions with each other. And so if two galaxies have black holes in their centers already, their black holes are eventually going to collide and coalesce. And so why is this important? This is very important and interesting because it turns out that when two black holes collide, so the two galaxies smash into each other, the stars kind of get mushed up and they settle down, but the two black holes do something even more dramatic. And you remember there are two punctures in space-time. And so when they merge, they actually cause entire space-time to shake around them. And those are called gravitational waves. And they have been detected, right? So they have been detected by this collaboration called LIGO, and I'll just show you that in a minute. I mean, this is such a beautiful simulation from one of my former graduate students. So the flickering that you see there is the black hole feeding, okay? And so you see these two very gas-rich galaxies merging, and their black holes are going to merge in the end, and things are going to settle down into some hot mess, and eventually it'll start looking like a much bigger galaxy when things settle down. But in the center, the black holes would still be rotating around each other, captured in each other's gravity, eventually will coalesce and shake, cause earthquakes in space-time when that happens. So this particular set of gravitational waves from supermassive black holes that are harbored in the centers of galaxies is yet to be detected. What we have detected so far is the merger of stellar mass black holes, the wimpy cousins of the guys that I am interested in, which are about 10 times the mass of the sun, 30 times, 50 times the mass of the sun. Remember, these guys are million to billion times mass of the sun. So that is yet to be detected, but we know that, there are tremors in space-time that are generated when any two black holes, we have proof of concept because these stellar mass black holes, their merger has been detected. So I just want to show you this movie just because, very, very early on, this is one of the first calculations. This is looking head-on into a galaxy where you have a very supermassive black hole in the center, and a second one has been plopped in as a result of that merging mess that we saw, the larger scale galaxy merging mess. So you see the second guy spiraling and making its way into the center. And there are lots of features that you see just to show you that these will all produce observational signatures, right? So that's what we're after. So when we're doing calculations, we want to see, we don't see the black holes themselves, but we can see the precursor, the postcursor, the aftermath of their collisions. So what really happens when two black holes collide? So these are state-of-the-art simulations using that incorporate Einstein's theory of general relativity, where you are seeing the merger of two black holes and how they create these earthquakes in space-time, the gravitational waves. I think you can see, and these are state-of-the-art, and this was a breakthrough that was made less than 10 years ago. The ability to do this computation. So we finally had the technical parts as well as the computational power available to do this. So this is work that we're doing. Remember, I told you that I'm very interested in understanding how galaxies and their black holes evolve. So these are black holes over cosmic time. That is just a clock. So on the on the y-axis, on the upper side, you're seeing the mass of the black hole. On the bottom is a property of the galaxy that it is sitting in. So this is just to show the data. The little black specks you see there are the data. So this is the correlation that we see between the stars in a galaxy and the black hole today. So people like me are working on building up the storyline of how does the first black hole form, how does it grow, and how do we end up seeing it, and how do we see a feasting black hole become a fasting black hole. So those are the key research questions at the moment. So remember, I told you that supermassive black hole mergers and the gravitational waves from them. In order to detect that, you actually need to be in space. So this is a proposed project by European Space Agency called LISA, and NASA is part of it, and I'm part of the NASA LISA science team. And so this should go up in the late 2020s, early 2030s. So we should see those first signatures of supermassive black hole collisions. Meanwhile, what has been detected are by this LIGO collaboration. These are the mergers of the small black holes in the nearby universe. And so this is just a graphic showing you how many events we've seen, everything we see in purple and blue. And right now, we're pretty much seeing an event a week. So it took 40 years for these guys. They were waiting, right, to have the technical capability, the accuracy, and the precision to be able to make this detection. And finally, they had a breakthrough a few years ago. And so the fact that gravitational waves exist has been proven, and so now we just need to wait to open the window with supermassive black holes. And the reason why things are slightly different, so basically you are going to need a configuration of 3 satellite systems that are going to go around us, and where any distortion of space-time will then be detected. Right? So this is the configuration that is planned for LISA. So one of the exciting things about supermassive black holes is that in addition to seeing the gravitational waves, as I showed you with my little calculation of the gas and how things fall in, you would see other electromagnetic. You'd have a siren, you'd have some X-ray flare that's showing you, so that's a place we can localize them much better than we can these little black holes, because you know where a merger is happening. There'll be other signatures in optical, X-ray, infrared, radio wavelengths, and we have all of those telescopes. We're soon going to have James Webb Space Telescope that's going to open up the window of the infrared universe. This is a part of wavelength part of the universe, a set of glasses that we have not looked at the universe with all that much. And these are glasses that are going to allow us to see farther than anywhere before because these rays cut through the dust. And the early universe is very dusty. So I want to close with a personal note, which is something that was very exciting that happened late last year, is that when I was a graduate student in Cambridge in 1998, I wrote this very speculative paper, right? At the time, we didn't know as much about how this little black hole connects these very large scales, how does it impact the big sort of region around itself and shape the galaxy. So I just came up with a speculative picture where it was very clear for a black hole, in order to impact these large distances, it had to drive a wind or an outflow or something that would physically reach far away from it. So I postulated there would be these things called quasar outflows and predicted a very unique signature in the radio wavelengths for the blobs of matter that this black hole jet would push out. And a geometry for it. It would be symmetric around the black hole. That would be an active quasar that's feeding. And what was peculiar about this was the wavelength at which the signature would be seen, so 900 gigahertz. So it's very much in the radio. There was no instrument available then. So this was a prediction, right? And I knew that there was a plan to make an array of radio telescopes called the ALMA array in Chile, but it was really on the books at the time. It hadn't become real. But 3 years ago, that array got built. And about 2 to 3 years ago, that array had the sensitivity to detect these objects if they were there. I moved on into other things in black holes. I was not waiting for this. So it was wonderful. Late last year, I suddenly got an email late at night saying that we've actually detected one such object that you predicted. And uncannily, the cartoon, yeah. So uncannily, the cartoon geometry is just, it's crazy. So Mark Lacey and his collaborators, Mark wrote to me and said, how the heck did you dream that configuration up? I said, well, it was just a physics calculation. And he said, it looks exactly like. So I just wanted to show you that cartoon and the actual data. So, a life in science, for the young people in this room, I just want to tell you, life in science is fantastic. And what is fantastic about doing science right now is that for the first time in a very long time, within one human lifespan, you can make a prediction and there will be instrumentation. Hopefully your colleagues will be interested enough to follow. Let's assume that they are, right? Then within a lifetime, that prediction can either be validated or invalidated. It's cool either way. Just imagine, right, that somebody's built, there's an instrument that can check out an idea that was made as a prediction. So this is just an example to show you, it's a long wait, it's 20 years, and I wasn't watching the clock, I was doing other things, but it's just a fantastic profession to be in. So I really encourage you to think about being in basic sciences. We need a lot of young, bright minds to do that. And there is no technology without basic science, So in order to have all the technological advancements that we've had, basic science discoveries have been at the bottom of all of that. And we now have really important big problems that are impacting all of us. We need some really bright minds to start solving these global problems, most urgent of which, of course, is climate change, right? So I think getting bright young people to work in basic sciences as well as technology is really what we need for the future. So thank you very much for your time. So just go ahead.
Well, thank you for that. I think it's very clear, not only is the science exciting, but the importance of having ideas and then checking those ideas with observations, and that applies across many different disciplines. We have a few minutes left of our time here. I think what we'd really like to do is hear questions from the audience. I don't know if there's someone with a microphone or not that can pass it around. So I think
we have a roving microphone.
Yeah, so let's start. The first hand went up in the middle, and then let's work our way down. So so the 1, 2, and 3, please.
Presentation. Two related questions regarding the image of the black hole. One was you mentioned that it was like the photon orbit. Why was it not a consistent look to it? It looked like it was brighter in the bottom quadrant of the orbit. Why would they not be almost consistently the
It's
same?
the geometry of how we are viewing it.
Okay.
So things are not quite tilted flat.
And then the second question would be, why would it not also be almost like an electron cloud around the black hole? In other words, it looks like a donut as opposed to like all around, like a sphere.
Oh, you mean why isn't the inner part kind of filled? Once again, that has to do with the sensitivity of what they were able to reconstruct of the image. So there is stuff there which is much lower intensity, which is very hard to reconstruct. So you would have seen that. Yeah,
Thank you.
it's a good point.
Thank you for your question. Well, we're going to go here and then come down to the front. And I think given that we've only got 5 minutes, we may not be able, I'm afraid, to get to some other questions. I believe there's a book signing.
Yeah, so I'm going
And
to
so there'll be an
outside.
opportunity to perhaps ask you a question then if Priya is willing to answer it. Please.
So, does the pull of the black hole, is it possible that it would ever just eat up its own galaxy? Its own?
No, yeah, so the black hole itself is, it's very compact, and its mass is really small compared to the mass of the stars in a galaxy. So it's never quite going to collapse and eat and destroy the entire galaxy. Yeah, thankfully for us.
Okay, I think we'll do these two more. Someone grab them.
Is the
Please.
universe expanding, collapsing, or oscillating? What's your theory?
Well, the universe at the moment, we believe it is expanding, and the expansion is accelerating. And as you all know, right, what that really means, that the distances between galaxies, so our galaxy is not expanding, but the distances between space is stretching, accelerating and expanding. Exactly what the ultimate fate of our universe will be at late times is not known. We know that's what's happening right now. That is dictated by the nature of what this dark energy is. We don't really know. There are many possibilities, possible endings, depending on what exactly dark energy is. But we do know quite well what the universe is doing right now, and that is accelerating expansion.
Thank you for the presentation.
Thank you.
Talking about the dark matter or the dark energy, as you mentioned, overwhelmingly what exists really is dark. And my question about dark matter would be, does that matter exist all over the place, or is it somewhere out there which we detect? And if it does exist everywhere, even right here in this hall,
Yes.
then then the way we detect,
Right.
as you
No,
mentioned,
I get the way
can
the
that
way
be
you're going.
detected using Newtonian physics?
Yeah. So it's a great question. So dark matter is basically smeared everywhere in the universe. It's very lightly smeared in some places, and there are a few places that are sort of devoid of dark matter. Few voids, they're called. But most of the universe is lightly smeared. And there are regions where dark matter aggregates because of gravity. It turns out those are the regions where stars end up forming, galaxies end up forming in the universe, right? And yes, there is dark matter that's going through. This is one of the reasons it's been so challenged to detect dark matter. It doesn't interact with anything else. The only interaction so far we have realized that dark matter is likely to have is gravitational. So it aggregates with gravity, doesn't seem to have charge, so it doesn't interact with either light or any other charged particles. It may interact with itself beyond gravity with what's called a weak force, maybe. But so far, so in a way it's been kind of lucky, right? Because there is dark matter going through. There's not a whole lot of dark matter by the time you reach the solar system distance in our Milky Way. So it's kind of thinned out a little bit. So it's heaped in the center of the galaxy, thins out a little bit, but it extends way beyond where the light is in our galaxy and every galaxy as far as we know. But the rate of particles going through, right, is tiny, it's so sparse that it's so hard to detect. Besides, it does nothing, thankfully, right? So there are dark matter particles that have gone through us. Imagine if it would reconstitute the atoms or something, then we wouldn't be here, right? So that's sort of been one of the reasons it's been very hard to detect dark matter.
So
there's one question from.
I'm so sorry.
Really?
We have such a full schedule. I hate to interrupt this.
Okay, I'll catch you later.
I do appreciate all the questions. It shows it's a great testament to the topic and to our speaker. So please, thank you.
Thank you so much, everyone. Thank you.